Hey, you guys, how are you? It's Roger again. I can't remember if I told you before or not, but I do have a background in diving medicine. I was a Navy diver medic, treated hundreds of divers in the recompression chamber. I'm also a certified hyperbaric technician and a diving medical technician instructor for the National Board of Diving and Hyperbaric Medical Technology. I'm only telling you this because this lesson that we're going to kind of cover today is related to decompression theory, and it does tie into decompression sickness a little bit. I'm not going to go into that too much, but it does, and I wanted you to know that I do know a lot about this. The one thing I wanted to remind you though is just like the physics. You guys have the slides, you're going to go through it yourself. This is more of a generalized go through related to this topic and kind of hit some high points, maybe kind of explain a few things here and there, okay? All right, so let's go ahead and get started. So again, we're going to talk about introduction or decompression theory, all right? This is introduction to decompression theory. And we're also going to talk a little bit about the history as well, just some important times in history related to decompression and decompression theory. So basically, when you're going to talk about whether it's decompression sickness or decompression theory, in the sense of whether a diver is at a point where it's a risk or not, you have to take certain things into account. And basically it's the gas exchange, specifically, right, inert gas exchange. O2 isn't really a problem, right? Even though it can form bubbles and all that, we metabolize O2. So it has to be more of an inert gas, or a gas that just doesn't play, any particular role in the body, other than it's just trying to make up, a certain amount of partial pressure to make up, the 100% of the gas that you're breathing, or mixture of gases that you're breathing, okay? But inert gas exchange, and then if you do form bubbles, how does the body handle those bubbles? Because even though the body's really good about filtering out bubbles every time we dive, if it's too much or they're too big, then they're gonna cause problems, okay? And then if it does cause decompression sickness, what's the resolution? What do you do about it? So some important points in history that I believe are significant. You look at Robert Boyle, and I think if you think back to the physics topic that we talked about not too long ago, I'm pretty sure I mentioned Robert Boyle, but if not, Robert Boyle's law, right? In the late 1600s, basically he put a viper, or a snake, if you will, in a little chamber that he had. He called that chamber an exhausted receiver. And basically what it wasn't really a chamber where it pressurized the animal, but rather it exhausted the pressure within that chamber and it took it to altitude. So really it was a hypobaric chamber, okay? So it just relieved the pressure within that chamber and it took that snake to altitude. And then what's significant about that during those experiments that he was doing was that in that particular experiment, a snake developed a bubble in the white humor of its eye, and some of that literature says that the snake was exhibiting signs of pain or whatever, but whether it's true or not, don't know. But there is writing that says that he did notice that bubble in the eye. So to some degree, that was probably the first time that somebody wrote something down about gas bubbles coming out of solution and causing a problem within the body. The next one is trigger. This is significant because this French engineer actually developed a caisson, or a pressurized container environment, that people could lock in and out when they were mining, you know, in this case, sometimes in the rivers, but they were basically pressurized environments that people could lock in and lock out of. The thing that's significant about this is that during this time period, when those workers were in those caissons, they were in there for, you know, hours, okay, because they were working. And when they were done and it was time to go home, nobody was thinking about decompression. You know, it was a pressurized environment, and nobody was thinking about anything like that. So these workers would then lock out. They would relieve the pressure without any decompression stops, and then, you know, they would leave. And nobody was thinking about any problems. So as time went on, more and more of these workers were starting to exhibit signs and symptoms of what we know now to be decompression sickness. All right, so they were experiencing joint pains, numbness, you know, and what have you. That was another significant time in history where someone actually documented something that was important to get us thinking about, hey, if we're working in a pressurized environment and then leave, there could be problems, okay? So that's why that's significant. The other thing that's significant about that is he invented the caissons, those pressurized environments or containers. And I think it's later on in the lesson plan, but while I'm talking about it, you know, I might as well get it out of the way. But what's really interesting about that is that this concept of those caissons was actually used in other construction projects, and one that is significant is the Brooklyn Bridge. What's cool about this, I thought this was interesting, and I know this is kind of off topic, but even though this guy invented it, the people or the company that was using his invention to build the Brooklyn Bridge were actually the first company that got the patent for these caissons, which, you know, he doesn't get much credit for inventing the caissons. And then also the Brooklyn Bridge is there, so there you go. And then you have Paul Burt. What's important with Mr. Burt here is one or two things, that whenever you know, when we got to the point where we understood decompression sickness better, that we knew, let's say it was a bubble related disease, these three bullets down here, what's really important with Mr. Burt here is that, one, he suggested that recompression should be the treatment or the resolution for decompression sickness. And then he also suggested to slowly decrease pressure in order to decrease the risk of these bubbles coming out of solution, okay? So he basically suggested a slow ascent or slow reduction in the ambient pressure to lower the risk of decompression sickness. And then this one is really important. He was the first to suggest decompression with oxygen and also recompression. So the use of oxygen to deal with the risk of decompression sickness. And then J.S. Haldane is another important figure in history related to decompression, and I think I talked about him in the physics lecture a little bit, but basically he was commissioned by the British Navy to develop decompression tables or schedules. So in the end, he is known as the father of decompression, staged decompression. One of the things that we should note with his research and experiments to come up with a set of decompression tables that were going to work for the Royal British Navy divers is that when he was doing his experiments with animals, he started with different animals, but eventually he ended up with goats. But what he was able to figure out from his experiments is that the body, in theory, the human body could tolerate a 2-to-1 reduction in atmospheric pressure. And that's what this is right here. Found that a 2-to-1 pressure ratio decompression rule was generally safe. What that means is that he felt, in theory, that since the body can tolerate a 2-to-1 reduction in atmospheric pressure without any increased risk or signs of clinical decompression sickness, basically, if you're at 33 feet, and this is 0, this is 2 atmospheres absolute, right? 2 ATAs. You can go from 2 to 1, okay? 2 to 1, 2 to 1 ratio without signs and symptoms of decompression sickness, or with a low risk of decompression sickness. All right, that's what he basically came up with. And then from there, he just took it to any other depth and then developed those decompression tables, decompression stops. So in theory, this is what he came up with. He believed that if you went to 8 atmospheres absolute and you could do a 2-to-1 reduction safely, my next stop should be by half. So I should stop at 4 atmospheres absolute first and get rid of some excess inner gas before I do my next reduction in atmospheric pressure. So half of 8 is 4, okay? So by half, 2-to-1. So my next one would be 2 atmospheres. That would be my next stop. So if I made a dive to 8 atmospheres, this is just, talking. If I made a dive to 8 atmospheres, then my first decompression stop should be at 4, and I should stay there for a certain amount of time until I get rid of some excess inner gas, so it's safe to move to my next one, okay? That's basically, the Haldanian theory, and he's known as the father of stage decompression because of that. A lot of things in history related to decompression theory, decompression tables that were developed after Haldane did this were rooted and based off of his theory, okay? Yes, it's gotten better, of course, with technology and all that, but a lot of it has always been rooted in, out of his theory, okay? Real quick, probably this is better. So, related to his experiments too, and he basically theorized that tissues could be compartmentalized for the decompression theory. Okay, so he came up with tissue half times, which if you look at your slide, right, he came up with 5, 10, 20, 40, and 75-minute tissues. We can go up to 500, 800-minute tissues these days if we wanted to, but anywhere from 5 to 120-minute tissues or a little bit more, after about 24 hours, everybody's considered saturated, right? But basically what we're saying is that if this was a tissue compartment that we're worried about, whether it's adipose or fatty tissue that we want to talk about, or we're talking about muscle tissue, it doesn't matter, just some type of tissue, but it's a 5-minute tissue. According to his theory, if we made a dive and we increased the pressure or the partial pressure of the gas that we're breathing, okay, basically in 5 minutes that tissue would be 50% saturated. 5 minutes later, you cut this in half, and it would be 50% saturated of what was left. And 5 minutes later, it'd be 50% of what's left. And so on and so on. So somewhere around 6 tissue half times, you would be considered saturated, okay? Um, you can go up to 9-minute tissues these days. Don't worry about it, but roughly 6 tissue half times. Any tissue you take into consideration, you can consider it saturated. Okay. Real quick, even though, you know, a lot of divers think about decompression stops in the water and stuff, which is true, of course, but over time, eventually, you know, people came up with the idea of surface decompression, what is known as SURDO2s, surface decompression using oxygen. Like my experiences was when I was diving with the military, when we used to do SURDO2 or surface decompression dives. The way it works is, let's say on a normal schedule, normal table, you made a certain dive to a certain depth for a certain amount of time, and let's say it had decompression obligations, and it had a 30-foot stop for 5 minutes, it had a 20-foot stop for 15, and it had a 10-foot stop for 30. Okay, that's a lot of extra time in the water, being exposed to the elements, especially if the water's cold, things like that, or it's rough conditions. So surface decompression was good because you can shorten the decompression time because you throw in breathing oxygen, okay, versus air that the diver would typically be breathing during those decompression stops, right? The other thing is you go into a dry environment in the recompression chamber, and it's a much more controlled environment. You control the temperature, you can give them something to drink, you can keep them warm. So it's a lot more convenient and a lot less riskier to do surface decompression if it's done right, because you can control those other variables that can put divers at a higher risk to get decompression sickness, right? So the way a surface decompression dive would typically work is you do the dive, but then you would go to like 40 feet and that would be your stop. And then let's say you spend 5 minutes at 40 feet, and then you can make a direct ascent from 40 feet to the surface during a predetermined amount of time. That would be 1 minute. Basically, when we're doing surface decompression dives, you have 5 minutes to leave your last stop, which is 40 feet, and to get down to 40 or 50 feet in the chamber. All that needs to take no more than 5 minutes. So you have a 1 minute ascent from your last stop, which is 40 feet. That's 1 minute. Now you have 4 minutes left. When you get to the surface, you basically have really 3 minutes and 30 seconds. The way the Navy did it, you had 3 minutes and 30 seconds of what we called undress time. So we would take the diver, we would sit him down, take the helmet off, take all the gear off, dry him off, and you know, we would try to do it in under 3 minutes and 30 seconds, so we would have a little bit extra time, okay? But you know, in the end, you had 3 minutes and 30 seconds, and then you made the transition to the recompression chamber. You closed the door, and then you had 30 seconds to get them from the surface in the chamber down to 40 feet in the chamber. All right, that's basically the whole 5 minute deal, okay? 1 minute from your last stop in the water, 3 minutes and 30 seconds on the surface, plus 30-second descent, okay? Where you make up your time is in those 3 minutes and 30 seconds where you're undressing the diver, taking the wetsuit off, the helmet, and stuff like that. If you exceeded those 5 minutes, technically you would omit, it would be considered that you omitted decompression, and then it was no longer surface decompression dive. It would turn into a recompression treatment, and you're treating for omitted decompression, okay? But that's generally how it works, okay? So you have an idea. Workmen, this is a U.S. Navy captain, doctor that also came up with decompression theory and tables. You know, he just made some adjustments to J.S. Haldane's theory of stage decompression and stuff, and it just got better. And these were the first U.S. Navy decompression tables, especially the no decompression tables, which have been tried and true for many years. So that's the workman concept. There's also the M values. This is probably what is out there today, more and more. Yes, you have the computer models and stuff, but basically what the M values are, and it's a formula that is well beyond my mental capacity. But basically, what it is each depth, and I'm talking by foot. I mean, this thing can get that detailed. They could tell you, whichever tissue you want to take into account, whether you want to take 1 into account or you want to take 5 into account, they could tell you that a certain tissue at 50 feet shouldn't exceed this much gas tension of a certain inner gas. And as long as you don't exceed that M value, then you can come up to the next decompression stop. But they can give you 50 feet, 49 feet M value, 48 feet M value, and so on, okay? But just to keep it, simple, to the point, basically M value is a certain tissue gas tension value that shouldn't be exceeded before you make your next ascent to whatever your next stop would be, okay? Again, you still have the 5, 10, 20-minute tissues, all that stuff. We already kind of went over it. When you're talking about gas exchange, we're mainly, again, concerned about inner gases, all right? Primarily in diving, we, obviously we dive air, we use, nitrogen, but, with mixed gases, whether it's a tri-mix or even with the military and commercial dive companies, the helium is used a lot as an inert gas. So we're primarily concerned with inert gases, all right? The one thing to consider when you're talking about the risk of decompression sickness and all that is when you're using multiple inert gases, because they have different diffusion rates, they have different solubility properties. Like nitrogen is more soluble than helium in fatty tissue or adipose tissue. So all these things have to be taken into account, okay? If you're gonna look at it one way, it's better to just use one inert gas than two. But regardless, sometimes you use 2 inert gases. But that's what we're mostly worried about. Okay. It references Henry's law, right? Henry's law. The amount of gas that will dissolve in a liquid is almost directly proportional to the partial pressure of that gas. So, in other words, if I made a dive with air, and I'm using 79% nitrogen as the number to calculate and deal with, whatever depth it is, whatever that part, let's say it's a partial pressure of 1.58, eventually, if you stay there long enough, all your tissues are going to match that 1.5 partial pressure of that breathing mixture. When you're taking that nitrogen in at that depth, in the lungs, the tissues are going to match that. It has to be in balance. So, you guys know that every time you take a breath, you always take on a little bit more. So over a certain amount of time, if it's long enough, eventually 24 hours or more, it's going to match. It's going to be the same. If you're breathing 1.58 partial pressure of nitrogen, and that's it, that's the partial pressure of nitrogen in your lungs, after 24 hours, your body is going to have 1.58 partial pressure of nitrogen gas tension dissolved in your blood and tissues. It's got to balance out eventually. Let's see. Bubble formation. We talked about Boyle's law. Obviously trigger. When they started writing about people leaving those pressurized environment from work, and getting signs and symptoms of decompression sickness. Eventually, everybody figured out that, hey, this is a bubble-related disease. When we leave the pressurized environment, these bubbles form, they block blood flow, they distort tissue, they damage cells, they damage tissues, they occlude even the lymphatic system, and it causes problems, right? It causes decompression sickness. So here's the thing, every time we make a dive, even when we do no decompression dives, which is probably what most of you are probably accustomed to, even though it's a no decompression dive, when you get back to the surface and everything is okay, you're fine, you don't have anything wrong with you, it was a great dive, you're high-fiving your friends, you're posting everything on Facebook, what a great dive, all that stuff, you're actually super saturated. You have more dissolved nitrogen in your blood and tissues than what's in the atmosphere, our one atmosphere, okay? So that is a super saturated state. So every time we make a dive, even if it's a no decompression dive, you are always super saturated when you get back to the surface. The thing to point out here, though, is that excess nitrogen is not enough to cause problems, okay? Yes, bubbles are forming, but the bubbles are small. There are not a lot of them. And when they get to the lungs filter them out, and you exhale them over time, okay? The problem becomes when these bubbles are too big, there's too many of them, and they get jammed up in the vascular system, or they just kind of create a bottleneck, and they just congest the lung vascular system, and you have no gas exchange, and you can't breathe. And then you die from what's known as pulmonary decompression sickness. Now nobody wants to dive anymore, right? Just kidding. But that's the thing, okay? So we're always super saturated every time we make a dive. The question is that super saturation state, is it at a degree that will put us more at risk to decompression, for decompression sickness? That's the key. So bubble formation, you have de novo, or bubbles that just kind of form, just because the conditions are good for bubbles to just come out of solution and form out of nothing, or there are predisposing factors like adipose tissue can predispose people to decompression sickness. Also, working hard, too much CO2, injuries, problems with your blood flow or perfusion. All these things can be predisposing factors too that can put you more at risk to get decompression sickness, even if you did a no D dive and even if you did everything perfect. It could still happen, okay? And then there's also, what we consider pre-existing bubbles or bubble nuclei. Basically, it's a area or point somewhere in the body that is an environment for inert gas to move into, and then it's a perfect environment to form a bubble. Okay, that's what that is. It's also tribonucleation. It's also known as tribonucleation. We'll talk a little bit about that probably. Yeah, okay, so the tribonucleation, the thing with that, tribonucleation is basically an area of negative pressure that's created by movement of joints. So if every time, when you're going like this, the elbow, the knee, anything like that, in that joint, you basically create a negative pressure in the joint where if you make a dive, inert gas can move into there and it can become isolated from circulation. And then when you go to come back up or decompress, if the conditions are right, these bubbles can become isolated, like I said, from circulation, and then as you decrease the pressure around you, that pressure is in excess. of the ambient pressure, and it's going to want to come out of solution and form a bubble, okay? So basically, tribonucleation is a negative pressure area, basically in a joint, okay, that can predispose people to decompression sickness. And to give you an example, when I was in the military, if we were going to do a long deep dive or a decompression dive, they wouldn't let us exercise before the dive because of that. Because what do you do with exercise, right? You're moving your joints, you know, you lift the weights, whatever, right? So that joint movement causes that tribonucleation. So they wouldn't let us exercise because that puts you more at risk. You know, the vacuum phenomenon, all that's basically associated with tribonucleation, but these bubbles here are just extravascular bubbles. These are bubbles that are outside the vascular system, basically in a tendon, a ligament, and it basically distorts tissue, tears up tissue, you know, things like that. Going back to tribonucleation real quick, Evans and Walter, if you look this up, they actually have shrimp like on treadmills, and they actually have X-rays of crabs and shrimps when the crabs and shrimps are moving their joints and stuff, their little legs and everything. They actually can show you areas where bubbles actually form from that tribonucleation. So it's a thing. It's a real thing. Let's see. Basically, you know, let me just kind of, you know, put things in perspective with formation of bubbles. Basically, you have to have enough inert gas in solution to put you more at risk, and the conditions have to be there also for these bubbles to cause a problem. You know, could it be, you know, something where your perfusion is affected, okay? That's a predisposing factor. You know, is the water cold and you've been working hard? Because when the water's cold, right, what happens? You get vasoconstriction, so your perfusion is now affected. It's less when your vessels are constricted, you're not perfusing very well or as good as you should. When you're decompressing, that puts you more at risk. So basically, for bubble formation, you need to have enough inert gas that can cause a problem, and the conditions for that bubble to come out of solution, you know, and form a bubble, also have to be there, okay? Okay, so when you look at this isobaric counter diffusion, this is when you are diving with, let's say, multiple inert gases. You have gases moving in two different directions, okay? When is a condition like this, when does this present during a dive? So when you're shifting, what you call shifting gases or changing breathing gases, because you're at a different decompression stop at a different depth, and you need to change gases, okay? So basically, you were either diving helium and then you change back to air because you're shallower at a different decompression stop, or vice versa. You started off on air, which is not uncommon, okay? On deep mixed gas dives, you typically start on air and then you go down to 20 feet or 30 feet, and then you do a shift to your bottom mix, okay? So that's where you shift gases, but you can also do that at depth or at a decompression stop. So now you have two gases that have that are going in different directions, and they have different diffusion rates because they're heavier or lighter than the other one, and they have different solubility rates. So this isobaric counter diffusion can also be isobaric decompression sickness, because now you have these two gases trying, you know, to go in different directions, and at a constant, this is when you're at a constant depth, all right? You're not moving up or down, you're at a constant depth, but you're shifting these gases, and the sum of the two gases might come to a point where the sum of the two might exceed what's an acceptable level for the body at that depth, and then these extra, the extra gas tension, these bubbles are going to want to form, or these inner gases are going to want to form bubbles, and then it causes isobaric decompression sickness. Isobaric because you're at a constant depth. Okay, so that's what that's all about. So this is something that you have to consider when you're using two different inner gases and you're shifting them. Okay, so oxygen window. All right, so this is, what do we do about these bubbles that form, especially for resolution if you get decompression sickness? Okay, you guys might be familiar with the fact that if you make a dive and you get decompression sickness or arterial gas embolism, two different mechanisms of how it occurs, but in the end, both conditions have to go to the recompression chamber and get treated at depth with oxygen for a certain amount of time. Okay, it's a recompression treatment. That said, what you're doing is when you do recompression therapy, you're treating decompression sickness, you're creating an oxygen window, a big oxygen window. Okay, so what does that mean? Basically, you have the higher, when you expose these people to a higher partial pressure of oxygen, whether it's 50%, 20%, 30%, or 100%, okay, that's going to determine what that oxygen window looks like. In other words, I make a dive, my elbow hurts, people do an exam, they say, okay, you got type 1 decompression sickness, which is classic, which is joint pain, okay? That's type 1 decompression sickness. I go to the hospital, I get treated, they take me down to 60 feet in a chamber, and they give me 100% oxygen. 100% oxygen. Basically, I've eliminated the nitrogen, right? So I'm not taking in nitrogen into my body anymore. So I've created this huge pressure gradient, right? So I have 100% nitrogen in my lungs, 0% nitrogen in my lungs, but I have 80%, a partial pressure of 0.80 gas tension of nitrogen in my blood and tissues. At that point, my body's going to sense that and say, well, why do I have all this extra nitrogen in here? That's not it's 100% oxygen coming in. That's 100%. I can't go 110%. So the body says, I got to get rid of all this extra nitrogen. So the greater that oxygen gradient is, the faster we get rid of that inert gas, in this case, nitrogen, okay? That's your oxygen window, all right? I'm not sure if I should talk about this, but maybe just briefly. In saturation diving, the oxygen window plays a kind of a different role, because that was an example that I gave you when you're being treated for decompression sickness. The oxygen window does the same thing in a saturation dive, staying at the same depth. If you give somebody a higher percentage of oxygen to breathe, not necessarily 100% O2. So what happens is when they breathe that in, even if they're still breathing inert gas, okay, even if I'm breathing nitrogen in, because the oxygen partial pressure is a little bit higher, when I breathe it in, obviously we know that we metabolize oxygen, okay? And yes, the counterpart to that is that you increase the CO2 that's in your bloodstream and going to come out, that you're going to exhale from the oxygen you metabolize. But to keep it, in perspective into simple numbers, if I'm breathing 40 molecules of oxygen, when it gets, let's say I metabolize 35, I don't produce an equal amount of CO2 molecules coming out, okay? It's less. So if I metabolize 30 molecules of oxygen, I might only produce 15 molecules of CO2. So there's a gap. that gap has to equal 100% has to be made up with nitrogen or whatever inert gas I have dissolved in the tissues to make up that 100% coming back, okay? So for saturation diving, if somebody had decompression sickness, what that does is it can actually make a bubble smaller by pulling some of that inert gas out to make up that gap, if that makes sense, and then that bubble will shrink. Not because, we're not shrinking the bubble with pressure in this case, we're shrinking the bubble with an oxygen window because it has to make up the gap. The nitrogen is making up the gap from that oxygen that was metabolized that CO2 did not make up. And if that doesn't make sense just yet, we have a graph here that might kind of put it in perspective. So, if you look at this, right? So you're breathing this, so it's in millimeters of mercury. It doesn't matter, but just look at the numbers, right? So when we breathe in, okay, in this case, you got 570 millimeters of inert gas. In this case, nitrogen that you're breathing in. We have some water, and then we have 104 of oxygen, and then we already start with 40 millimeters of mercury, which is pretty standard. That's what we have right now, more or less, in our body right now, 40. And then it goes into the arteries, okay? If you look at, there's a little bit of a differential with the oxygen that transfers over to the arteries, but it's more or less the same, right? Now, when the oxygen gets metabolized, look at this, okay? This is in the venous system now, coming back, all right? So because this is at 1 atmosphere, right? So we're already saturated. It's still 570 coming out, right? 570 went in, 570 coming out. That's normal. That's inert gas. It does nothing but take up space, okay? It's a gas tension. That's normal. Water, give or take, normal, right? O2, look at it. We started with 104, right? But obviously we need oxygen for, cellular function and everything else, right? So we metabolized some oxygen. We started with 40 CO2. We metabolized way more than 5 with the oxygen, but we're only getting 45 of CO2. See, it's not a 1-for-1 mole here, right? It's not the same. Okay, so there is a gap, right? See up here, not 104, not 104 O2. That's not coming back. So what happens here? If we were trying to reduce a bubble size, or we're trying to treat somebody, that's where the oxygen window comes in. If we remove that bad inert gas, now we allow that inert gas to make up that difference, that gap, okay? And it gets some of that bad inert gas out, or it helps shrink the bubble by trying to give off some of that inert gas to make up that difference, okay? I mean, that's about as simple as this can be, put, okay? Hope that makes sense. But that's the oxygen window in a sense, okay? Let's see. We already talked a little bit about helium and mixed gas dives. Again, the counter diffusion thing, remember, you got 2 different inert gases with different solubility properties and different diffusion rates. We already talked about that. A little bit about surface decompression. I gave you, example of how that works. That's that. Basically, you go to 40 feet, then you come out, then you go on 100% O2 for a certain amount of time. Basically, instead of doing decompression in the water, you're doing it in the chamber, breathing 100% oxygen. So if that same dive, you would have done decompression in the water, you would have had 40 minutes of decompression in the water. In the chamber, maybe you only have 15 minutes because you're breathing O2, okay? And you're in a warmer environment, more controlled, and all that good stuff. We already kind of covered that, so I think you get it. All right, as far as saturation decompression, for the most part, just think about someone being saturated. When you make a dive, someone is going to be saturated to the depth, whatever it is, whether it's 50 feet, whether it's 100 feet, whether it's 300 feet, it doesn't matter what depth. Think of it like this: after 24 hours, someone's going to be saturated to that depth, or equal to all the partial pressures of that depth, of that gas that you're breathing, okay? So as far as decompression goes, let's take Aquarius, obviously, as an example. The Aquarius decompression schedule was developed back in the 70s, especially by the NOAA program, to use for a lot of different air saturation diving that was going on, habitats and stuff like that, okay? So anyway, it was developed a long time ago. It's tried and true, but now we actually use oxygen these days. We added oxygen. It's the same air schedule. It's still the same. We could still do it, breathing air. So nothing changed as far as the ascent rates and the travel rates. We basically start at 1 foot every 6 minutes, and then it changes, and it starts at 37 minutes per foot, 30 minutes per foot, and then it slows out all the way up to 37, 38 minutes per foot as we get closer to the surface. All in all, taking Aquarius as an example, as an air saturation system, air saturation decompression schedule, at 50 feet, after 24 hours, we're considered saturated to that depth. So whether we stay 3 days or 30 days, the decompression schedule, the decompression requirement time is still the same. That's 15 hours and 45 minutes, okay? You can use different decompression schedules depending on your breathing gases and stuff. There's companies out there like Comex, the French, the Brits, all that stuff. They have decompression schedules for mixed gas diving, of course, the military and stuff. But, air saturation is a lot simpler. When you get into these mixed gas diving, saturation diving systems and companies and military and all that, it's very complicated. You have to have treatment gases. You have to have emergency gases backed up for depth ranges, and it can get very, very expensive. Well, it is very, very expensive. So, as a whole, Aquarius, even though it's expensive, it's not as complicated just because we're doing air saturation diving. It's fairly simple considering. But when you're saturated, you're going to have decompression obligations. The good thing about that is that whether you stay, again, 3 days or 30 days, it's the same. So that's good in that sense. The other good thing about saturation diving is that you get what everybody likes to say and refer to as the gift of time, okay? Whatever your storage depth is, the storage depth is your living depth, the depth that you're saturated to. Then from there, you can make downward excursions or you can make upward excursions up to a certain point for a certain amount of time. So let me give you a good Aquarius example, okay? Since our storage depth is 50 feet, we're saturated to 50 feet. Consider 50 feet 1 atmosphere for those divers. So since we're at 50 feet, saturated to 50 feet, we can make a dive to 90 feet for 6 hours, okay? 6 hours. That's only because if you look at it, 50 to 90 is a difference of 40 feet, okay? From Aquarius, from that saturated storage depth of 50 feet. It's only a 40-foot difference. As opposed to diving from a boat on the surface to 90 feet, that's a 90-foot difference. Okay, so, diving air, you might only have 20 minutes at 90 feet, 15, 20 minutes, because it's such a difference in pressure, okay? So we go from 20 minutes of dive time with air, mind you, to diving out of Aquarius, 6 hours at 90 feet, still breathing air, using the same breathing medium. That's a huge difference, huge advantage for, companies, researchers, military, to be able to get a lot of work done at 90 feet from, Aquarius or a saturation system versus from a boat. Okay, I hope that makes sense. But that's why saturation diving, for certain groups or for certain projects, for certain things, is so beneficial, because you get so much more time to be able to go out there and work at a certain depth than you would from a boat. So when it comes to decompression, saturation diving, nothing really changes with respect to taking the same things that you do into account for regular diving. And I'm talking about oxygen toxicity and things like that. So, let me give you Aquarius as an example. Okay, we're at 50 feet, but we're breathing air, right? So let's take oxygen into account and use it as an example and go back to your physics. See, you probably thought your physics wasn't going to be applicable, but it is. All right, so let's go back to your physics. So we're at Aquarius, we're at 50 feet, and we're breathing air. So obviously we have 79% nitrogen. Let's just leave it at 21% oxygen. So using your T formula, remember your T formula from physics. Okay, here would be ATA. All right, so Aquarius, our storage depth, our living depth is 50 feet, right? I told you that. 50 feet of seawater. So do your calculations, okay? What is the atmosphere's absolute for 50 feet? Let me get my calculator. I'm going to give you some time. Okay, you should have come up with 2.51. Okay, so we're at 2.51. I want to know the partial pressure of oxygen at Aquarius storage depth or living depth, saturation depth of 50 feet. Okay, so we already know that 50 feet is an ATA of 2.51. We're breathing air, okay? So we know now that air has 21%, okay? So if you remember your T formula, what goes here? Gas percentage goes in here, expressed in a decimal. 21%, move the decimal place over 2 times, 21, okay? You multiply across in the T formula, so multiply that, okay? What do you get? I'll give you some time. Okay, basically it's hopefully you got 0.52, okay? PPO2, okay? And the T formula, partial pressure goes up here, so obviously, that's your answer right there, 0.52. Okay, so what does that mean in the scheme of things, okay? All right, so the reason Aquarius is at 50 feet and it's okay to breathe air is because, and again, 50 feet, depending on the tide, because most of the time, depending on the tide and stuff, Aquarius can be anywhere from 44 feet to 50, 51, 52 on high tides. But even on the high tides, it's only for short periods of time, maybe 2 hours, 3 hours, 4 hours, nothing more than that. Most of the time, we're below this. Okay, so what is the significance of that? All right. Pulmonary oxygen toxicity is something that we have to consider. Pulmonary oxygen toxicity is not a consideration until we basically exceed 0.50 partial pressure of O2, okay? Obviously, the more you exceed that, the quicker it's gonna present itself, okay? But you need at least 24 hours. At 0.50, 0.51, you need about 24 hours of breathing that in order to start getting signs and symptoms of pulmonary oxygen toxicity. All right. So that's why Aquarius is at 50 feet, because we want to use air to breathe. But if we use 21% any deeper than this, eventually we're going to run into pulmonary oxygen toxicity. Okay. So these, just because you're doing saturation diving, it doesn't mean that you don't take normal things into consideration. The only thing is that, you normally diving air wouldn't really consider pulmonary oxygen toxicity, diving air, doing typical no-D dives to 100 feet or something like that. You wouldn't even consider central nervous system oxygen toxicity, diving air, because that's not even a problem until you get to 218 feet using 21% oxygen, okay? However, for saturation diving, because the duration of that exposure puts you at risk, then we have to consider it. So that's why we're not at 51. That's why we're not at 52. Although a no-D dive, you could do a no-D dive to 55 feet for an hour if you wanted to, and not worry about pulmonary oxygen toxicity, not worry about central nervous system oxygen toxicity. But on a air saturation dive, more than 50 feet, you do have to worry about pulmonary oxygen toxicity. Okay, I hope that makes sense. Let's see. Okay, we're pretty much at the summary part, so I got really nothing more. I hope you guys kind of enjoyed that. I hope I was able to maybe just point out, some important times in history and some details that are important related to this, this lesson topic, and maybe broke some things down that were, a little bit easier to understand. So hope you enjoy it, and I'll see you next time.